At 11:36 Universal Time on October 29, an event slated to be invisible will reach its most critical point. An interstellar visitor, racing through our solar system at staggering speed, will swing past the Sun at closest approach. For months the public narrative was simple and consistent. Perihelion would happen behind the Sun from Earth's viewpoint. Solar conjunction, they said. No eyes, no witnesses. The window when any craft would perform its most fuel-efficient maneuver would fall inside a blackout. Wait until early November, officials told observers, then report back. 4 days before that moment, an amateur group proved the blackout story false. On October 25, a small team called Earth Exists published time-stamped telescope images and coordinates showing the object clearly visible near the Sun in daylight. The Sun occupied the same frame. Venus appeared on the edge. A reference star provided positioning. The object predicted to be hidden was instead separated from the Sun by a measurable angular distance. The raw data contradicted months of public statements. Geometry matters. Solar conjunction describes approximate alignment in celestial longitude. When an object lies within the Sun's glare, observations become impractical without specialized coronagraphs. But the October 25 observation placed the visitor at right ascension 13 hours 38 minutes and 44.9 seconds and declination 7 degree 4032.5, distance 2.34 astronomical units, apparent magnitude 15. Telescope access required, yes, but visibility undeniable. If an object sits in the same field as the Sun with a clear angular separation, then the claim about complete obscuration fails. That contradiction splits the world of explanations. Either orbital calculations from major institutions were badly wrong, or the narrative about invisibility had a motive beyond simple error. The amateur dataset grew into a pattern. Previous observations from October the 21st and 23rd showed systematic deviations from Jet Propulsion Laboratory predictions. Position offsets reached 15.4 arc-minutes. Lateral velocity components implied non-gravitational acceleration near 3.95 km per second. Brightness ran between 20 and 26% dimmer than models predicted, even as it approached the Sun. Over 48 hours, the object's right ascension shifted by 3/56 of arc and declination moved 17.7 north. Distance decreased by 2 cents and brightness increased by 0.04 magnitudes. Those numbers matter. 15 arc-minutes is large. 1 degree equals 60 arc-minutes. The full moon spans roughly 30 arc-minutes. When an object appears that far from its predicted track, something is changing its path. Brightness trends add another puzzle. Move a passive reflector from $2.36 to $2.34 and inverse square law predicts a brightness change around 0.017 magnitudes. Observers measured 0.04 magnitudes. The object brightened faster than simple distance change would produce while remaining substantially dimmer than model forecasts. Angular velocity increased over successive observation windows. Lateral acceleration persisted. The composite behavior fails to fit the simple model of a passive ice body following a ballistic trajectory under gravity alone. Institutional behavior fed the unease. In October, the United States entered a funding lapse that throttled NASA communications. SETI published revised post-detection protocols after a long hiatus in public updates. The International Asteroid Warning Network placed the object on a planetary defense list even though it posed no impact risk. A separate organization, EON, announced a 2-month training exercise starting 4 weeks after perihelion. Those actions, taken together with restrictions on public communications and instructions to avoid looking, felt like coordinated preparation for an event institutions expected to handle behind closed doors. The technical anomalies and the institutional reactions formed a pattern hard to ignore. If entities handling public information presented a story of unavoidable darkness at the most informative moment, when independent observers could demonstrate daylight visibility, motive must be considered alongside error. Perihelion is the time physics allows a spacecraft to exploit the Sun for momentum exchanges. The coincidence of an asserted observation blackout at precisely that window invited skepticism. At the same time, an altogether different object slipped into public view earlier in 2025. On August 2, observers Carlos and Raul de Lente Marcos reported a quasi-satellite of Earth designated 2025 PN7. Quasi-satellites are not true moons. They orbit the Sun, yet stay near a planet because orbital periods match closely. Such captures are rare and typically transient. This object had been in a quasi-satellite configuration only since the 1960s, a timing linked to human spaceflight. Researchers traced trajectories backward and found a striking match with Zond 1, a Soviet Venus mission launched April 2, 1964, which suffered failures shortly after launch. The Block L upper stage, a 3.2-meter wide cylinder, would have separated and drifted. Trajectory reconstructions placed 2025 PN7's orbital elements into a configuration compatible with a Block L fragment that failed to perform a full burn. Displacement numbers and inclination shifts fit a scenario where partial burn, emergency mid-course correction, and decades of perturbations produced a quasi-satellite today. Brightness estimates for a reflective metallic cylinder match observed magnitude within plausible uncertainty. Spectroscopy would settle origin questions. Artificial metal alloys show clear signatures distinct from silicate mineral spectra. In 2020, a similar case resolved when the Pan-STARRS team and infrared spectroscopy revealed stainless steel from a 1966 Centaur stage. For 2025 PN7, confirmed metallic lines would identify human hardware. Silicate signatures would support a natural origin and reintroduce coincidence questions. Why does a natural quasi-satellite appear when humanity first launched deep space missions? If spectroscopy returns unknown or non-terrestrial signatures, the implications escalate. No spectrum arrived for months. Scheduling constraints on major telescopes offer a plausible explanation, but silence fed conjecture. 3 objects reached public attention in 2025 with anomalous properties. 2 of those anomalies sit in orbits advantageous for surveillance or easy follow-up. The statistical patterns invite alternative hypotheses. If interstellar probes exist in some abundance, placing a monitor in a quasi-satellite orbit while deploying a fast flyby probe makes practical sense. Inside the civilian research community, another line of preparation unfolded. The Galileo project installed a triangulated camera array on top of Sphere, the massive entertainment dome in Las Vegas. Sphere sits high, unobstructed, in a region of clear skies and nearby restricted airspace. The project deployed infrared and visible cameras, machine learning algorithms trained to distinguish drones, birds, planes, satellites, and truly anomalous behavior. Triangulation at 3 sites gives 3-dimensional position, velocity vectors, and acceleration profiles. The system flags objects that accelerate beyond known propulsion limits, make improbable turns, or hover without visible lift. Unlike classified sensor teams, Galileo intends to publish data and analysis openly. The timing of that installation was notable. Public mention on a major podcast came 5 days before perihelion and 4 days after amateur observers proved daylight visibility. Sphere's array would record airspace above a major city with independent measurement and transparency. If smaller probes deployed and passed over Nevada, Galileo's instruments would gather evidence accessible to independent analysts. Combining public instrumentation and grassroots observation produces a disclosure pathway that bypasses traditional classification gates. Scientific anomalies surrounding the interstellar visitor sharpened the question of origin. Researchers enumerated 8 independent observations that resist neat natural explanations. The object's trajectory aligns with the ecliptic within 5 degrees, an unlikely arrival geometry for random interstellar debris. The flyby path will pass unusually close to Venus, Mars, and later Jupiter, a chain of planetary encounters reminiscent of deliberate mission planning. The solar conjunction timing overlapped perihelion in ways that initially suggested intentional concealment. The object exhibited an antitail, material projecting sunward, uncommon in comets except under specific geometric conditions. Spectroscopy revealed nickel vapor in the coma with a curious absence of iron. James Webb observed a carbon dioxide-dominated composition with CO2 to water ice ratios near 8:1, unusually high for known comets and suggestive of formation in ultracold regions or selective volatile choices for engineered behavior. Activity began at distances beyond typical comet activation thresholds, with outgassing detected near $6.40. Coma morphology showed geometric patterns inconsistent with random jets alone. Taken separately, each anomaly has plausible natural mechanisms. Combined, they produce probability estimates that lean away from coincidence. The debate among scientists centers on priors. If probes are vanishingly rare, natural explanations dominate. If technological emissaries are plausible at non-negligible rates, the technological hypothesis gains weight. Objective resolution requires data that distinguishes powered maneuvering and controlled emissions from passive sublimation. Military testimony and congressional scrutiny added another layer. Sworn statements from trained observers recounted objects performing maneuvers beyond known aerodynamic limits, disappearing from radar, surviving kinetic impacts without fragmentation, or hovering silently over secure installations. The All-Domain Anomaly Resolution Office and other bodies produced reports that emphasized lack of evidence for extraterrestrial origin, yet whistleblowers alleged active recovery programs and material analysis under heavy classification. The National Archives' deadline to consolidate UAP records loomed amid partial compliance and persistent redactions. Critics argued classification often protects institutional control rather than national security. Those dynamics matter because classification structures determine who sees what and when. If genuine unknowns exist in classified repositories, independent verification becomes difficult. Whistleblowers who follow proper channels face career risk when investigations conclude with non-disclosure or dismissal. When trained witnesses take testimony to Congress, public pressure grows. When independent, transparent systems like Galileo collect measurable anomalies, classification loses power over raw observation. Meanwhile, Webb produced discoveries that reframed cosmic context. 2 PhD students in Sydney developed Amigo, an algorithm that corrected subtle electronic distortions in Webb's infrared imagery, restoring diffraction-limited resolution without a physical servicing mission. With improved interferometric performance, Webb refined spectroscopic and imaging capability for the interstellar visitor. Webb's deep field surveys revealed hundreds of unexpectedly bright candidate galaxies in the first billion years after the Big Bang, objects that stress formation models. Webb exposed fine-scale structure in interstellar dust with patterns resembling wood grain and layered filaments shaped by magnetic fields. The telescope's growing catalogue of anomalies emphasized a broader truth. Cosmic phenomena exceed current theoretical comfort zones. Finding an engineered object in a universe already stranger than models predict would be surprising but not logically impossible. Observational schedules offered concrete tests. JUICE, on course for Jupiter, would pass within observational range 5 days after perihelion, carrying instruments able to capture composition, magnetics, and particle environments. Earth-based approaches expected close-pass observations on December 19 when the object neared 269 million kilometers. Juno, in Jovian orbit, pledged to listen for radio emissions during a March encounter. If structured radio signals appear, those would count as strong evidence of artificial activity. Radio detections provide a different axis of proof than imaging and astrometry. If perihelion produces simple cometary behavior, brightness matching inverse square modified by sublimation physics, trajectory consistent with outgassing accelerations, coma morphology driven by rotation and stochastic jets, then the technological hypothesis loses traction. If perihelion reveals lateral accelerations inconsistent with passive forces, synchronized brightness modulations, geometric emissions, or release of secondary objects that follow powered trajectories, the scientific conversation changes rapidly. Multiple independent observers recording the same anomalies would force open investigation, not via sensational headlines, but via peer-reviewed analyses and mission planning. The next 6 months would yield stacked measurement opportunities: JUICE's November window, Earth close approach in December, Juno's radio listening in March. Wider implications threaded through every possibility. SETI faces methodological questions in light of non-detections and emerging biosignatures. Webb's detection of dimethyl sulfide in an exoplanet atmosphere highlighted progress toward biosignature chemistry while reminding researchers about ambiguous abiotic production pathways. Theoretical work on typical distances between technological civilizations produced sobering medians in the tens of thousands of light-years. If those distances hold, probes arriving in our system could be ancient relics or hardware built to endure timescales far beyond biological lifespans. Alternatively, life abundant in diverse environments expands the probability space for technological emergence. The dark forest hypothesis proposes silence as survival strategy. An alternative view envisions a galaxy of explorers using physical probes rather than omnidirectional broadcasts. None of these speculations resolves observation into narrative. Science progresses by measurement. Tomorrow's perihelion will either strengthen the case for natural origin or produce anomalies that demand deeper inquiry. Data will arrive from public telescopes, space missions, amateur observers, and projects like Galileo. Spectra of 2025 PN7 will confirm or reject human hardware hypotheses. JUICE and Juno will provide additional axes of measurement. If small secondary objects appear in inner system volumes, ground-based and civilian sensor networks will document their paths. Classification mechanisms lose traction as citizen science supplies independent verification. This story is neither triumphant confirmation nor fearful alarm. It is an unfolding scientific episode. Evidence accumulates. Patterns emerge when datasets grow large enough to overcome coincidence. The stakes extend beyond single objects. If technological probes transit the galaxy at detectable rates, statistics will reveal that reality over time. If interstellar visitors prove natural, discoveries still refine understanding of planetary systems and cosmic chemistry. Either outcome expands knowledge. On October 29th, observation will proceed. Instruments will record. People with telescopes and with code will examine photons and trajectories. In 5 days and 5 months, follow-up windows will refine measurements. Over years, survey telescopes and improved analysis will build a catalogue of interstellar visitors. Each entry will clarify what travels between stars. The universe remains indifferent to our expectations. It yields answers to whoever looks carefully enough. Tonight, observers point their instruments and wait for data to speak. When the light from perihelion finally reached Earth, data poured in from every direction. Observatories from Chile to Hawaii, from Tenerife to Cape Town, all captured the moment 3I Atlas curved around the Sun. The object remained intact, a bright filament against solar glare, trailing a luminous coma that twisted like a ribbon in high-resolution frames. For the first time in history, an interstellar visitor's perihelion passage was recorded continuously across the electromagnetic spectrum: optical, infrared, ultraviolet, and radio. At first glance, the light curves appeared normal. Brightness peaked slightly before closest approach, then dipped. Comet-like behavior, nothing more. But as processing continued, patterns began to emerge. The object's rotational period seemed irregular, varying subtly across observation windows. A comet's rotation should remain steady unless torques from asymmetric outgassing act on it. Yet the frequency shifts were rhythmic, not chaotic, not random, as if driven by controlled impulses. Spectral analysis deepened the puzzle. Infrared readings from ground arrays showed brief bursts of heat inconsistent with steady sublimation. Temperatures spiked and cooled in intervals that didn't match sunlight variation. The intervals were too short for thermal inertia, too regular for natural jets. Something was modulating its emissions. By October 30th, independent teams began comparing positional data. The deviations were small, tens of kilometers at astronomical distances, but consistent across multiple tracking systems. The trajectory after perihelion no longer matched the purely gravitational model. A slow, measurable drift appeared, slight but undeniable. The object wasn't coasting exactly where physics predicted. In the following days, debate reignited. One side framed the deviations as outgassing asymmetry or measurement noise. The other called them course corrections, deliberate, efficient, timed with perihelion as if taking advantage of the Oberth effect. That possibility carried weight because the deviations pointed along a vector that reduced the object's outbound velocity relative to the solar system. Instead of escaping faster, it slowed fractionally. A maneuver that made sense only if the destination was within, not beyond. In November, as ESA's JUICE spacecraft approached its observation window, onboard instruments locked on target. Janus imaging delivered high-resolution pictures showing structured surface regions, flat planes reflecting light more evenly than irregular ice would. Spectroscopy detected complex carbon-oxygen compounds, metallic traces, and thermal emission patterns arranged in geometric zones. The official release described unexpected reflectivity gradients and non-uniform albedo consistent with exposed crystalline or engineered surfaces. The phrasing was cautious but heavy with implication. Meanwhile, radio silence held until Juno's instruments, orbiting Jupiter, registered something new. On March 16, 2026, the WAVES instrument picked up a narrowband signal near 1420 MHz, the hydrogen line. The signal pulsed in repeating sequences lasting 72 seconds, identical in duration to the 1977 WOW event recorded by Ohio State's Big Ear telescope. The modulation matched amplitude envelopes, frequency drift, even decay slope. Statistical coincidence seemed impossible. When cross-correlation confirmed that 3I Atlas's inbound trajectory originated from the same region of Sagittarius as the 1977 signal, the pattern snapped into focus. 48 years earlier, a message had come from that direction. Now an object from that same coordinate was transmitting the same rhythm. It was as if a question had been asked once by radio and answered later by arrival. Juno's data reached Earth 6 days later. Processing at the Deep Space Network flagged the signal as artificial in origin, not because of content it carried no obvious message, but because natural radio sources don't repeat precisely structured pulses with that kind of stability. Plasma oscillations, lightning discharges, magnetospheric noise all vary randomly. This didn't. Public release came slower than observation. Leaks preceded official statements. First, an anonymous source within ESA confirmed that JUICE's post-perihelion imaging revealed regular geometric reflectivity zones. Then an internal memo from NASA's Planetary Science Division circulated online, referencing non-ballistic motion at perihelion consistent with limited delta-v impulse. Within hours, the story spread beyond astronomy circles. Headlines filled with cautious phrases: possible controlled maneuver, interstellar visitor exhibits anomalous behavior, Juno detects structured signal. Governments scrambled. Spokespersons deflected, urging patience while data underwent peer review. Intelligence agencies issued temporary advisories restricting raw telemetry distribution. But the data was already public. Amateur observatories had recorded similar trajectory deviations. Open-source analysts replicated signal patterns from Juno's published frequency graphs. The genie was out. For the scientific community, disbelief fractured into two camps. One insisted on exhaustive natural explanations: outgassing jets mimicking impulse, instrument artifacts in Juno's radio receiver, coincidences exaggerated by confirmation bias. The other accepted the simplest interpretation: an object performing a controlled burn at perihelion, followed months later by structured radio emission consistent with deliberate signaling. By mid-April, triangulated radio tracking showed that the object's outbound velocity had reduced enough to remain bound to the solar system. 3I Atlas was no longer escaping. It had become a long-period body with an orbital period of roughly 160 years. The visitor had stayed. The realization triggered deeper questions. If a probe decelerated intentionally into a bound orbit, what was its mission? Observation? Data relay? Deployment? And if it deployed something, where had those smaller units gone? Answers came from a network of amateur satellite trackers weeks later. New objects appeared in low solar orbit, small, faint, moving against predicted backgrounds. At least 4. Their trajectories traced backward to the perihelion arc of 3I Atlas. Each one about 20 meters across, dark, radiating little heat. Non-reflective. Silent. Governments issued no comments. The US Space Command classified internal tracking logs. But independent radar arrays in France and Japan confirmed detections. Analysts called them unidentified near-solar bodies. Publicly, the story faded from mainstream coverage under the weight of economic and political noise. But in research circles, the silence spoke louder than any statement. Meanwhile, back on Earth, the National Archives collection remained nearly empty. Agencies submitted historical relics, nothing modern. Christopher Mellon's warning from the SOL Foundation conference echoed everywhere: the world is not ready. Whether that meant emotionally, politically, or structurally, no one could tell. But readiness no longer mattered. Observation had overtaken secrecy. By December, 3I Atlas reached its closest approach to Earth. Telescopes worldwide captured it glowing faintly in night skies. Spectra showed small shifts in emission lines compared to pre-perihelion readings. Nickel signatures strengthened. The object's coma displayed symmetry too precise for random outgassing, sharp-edged fans arranged at 120-degree intervals, rotating in phase with the body's tumbling. It looked engineered, though scientists avoided that word. Amateurs noticed something else: faint bursts of light, millisecond flashes repeating every 4.3 minutes. They looked like optical beacons, laser pulses perhaps, yet the energy level was low, barely above detection threshold. Still, their periodicity and stability defied natural explanation. By January 2026, the accumulated data was overwhelming. The official papers were careful, clinical, guarded: non-gravitational accelerations of unexplained magnitude, spectral anomalies consistent with metallic content, structured periodic emissions of uncertain origin. No conclusions, only observations. But conclusions formed themselves. Public awareness reached a threshold without anyone making an announcement. Forums, conferences, and news feeds converged on the same idea. Something not natural had entered the solar system, maneuvered deliberately, transmitted, and stayed. There was no single moment of disclosure. There was no speech. There was only data. And yet, no catastrophe followed. Civilization didn't collapse. Panic didn't spread. People went to work. Children went to school. Markets opened. The extraordinary blended into the ordinary. Humanity absorbed the knowledge the same way it absorbs every new fact, slowly, unevenly, but permanently. Across observatories, a new protocol emerged organically. Track, record, publish. No waiting for permission, no central gatekeepers. A distributed network of observers connected by shared databases and automated reduction pipelines began mapping the small objects near the Sun. They catalogued each one, logging brightness, motion, possible communication bursts. Within months, a pattern appeared. The smaller units followed orbital planes intersecting Earth's path twice a year. Observers predicted the first close pass in August 2026. At the same time, Juno continued to monitor the faint 1,420 MHz emissions. The pulses shifted subtly in timing, forming repeating intervals that, when plotted, resembled a binary sequence, prime numbers. Nothing in natural astrophysics produces prime sequences. The message, if message it was, carried meaning, a mathematical fingerprint of intelligence. Back on Earth, the Galileo project's cameras over Las Vegas detected an unusual object at high altitude in late July. The tracks matched nothing in satellite catalogs. The object hovered, then accelerated horizontally at speeds far beyond known drones, leaving no propulsion signature. Triangulation confirmed the data. Within hours, analysts connected the observation to one of the predicted intercept points from the perihelion deployments. The loop was complete. From interstellar space to the inner atmosphere of Earth's skies, the trail remained continuous. What began as a supposed comet had become a network of observable phenomena linking orbital mechanics, spectroscopy, and radio astronomy into a single chain of evidence. Institutions responded cautiously. The European Space Agency scheduled dedicated follow-up missions. NASA proposed an interception probe, codenamed Horizon Sentinel, to match 3I Atlas's orbit and study it directly within a decade. SETI, meanwhile, shifted focus from listening for distant signals to monitoring local space for near-Earth transmissions. In universities, new courses appeared under names like interstellar archaeology and non-human engineering studies. Debates raged about ethics, contact procedures, and data transparency. The public, accustomed to decades of secrecy and speculation, now faced an abundance of evidence but no narrative. And so the story continued without an ending. 3I Atlas drifted beyond Earth's orbit, trailing faint artificial glints as sunlight struck symmetrical surfaces. The smaller units continued their silent circuits near the Sun. Juno's receiver kept logging pulses. The quasi-satellite 2025 PN7 maintained its watchful dance around Earth, spectroscopy still pending, still unresolved. Above Las Vegas, the Galileo cameras kept scanning, night after night, mapping the quiet sky for motion that didn't fit. No proclamation came, no confirmation from authority. Only an unbroken chain of data points, geometric, spectral, radiometric, describing a reality that no longer waited for belief. We had always imagined disclosure as an announcement. Instead, it arrived as observation. No one declared that we were not alone. The universe did.